Игнат расскажет, как избежать проблем при переходе на другую архитектуру. Он работает в Великобритании уже 4 года и поделится своим опытом. Спасибо.
Спасибо. Я буду рассказывать на английском, потому что я всей терминологии не знаю на русском языке. Okay, so I'll switch to English now. So thank you for coming to my talk. Today we're going to talk about how to make your software fail on ARM64. Okay. Oh no, it's worked. So a little bit about myself. I do performance and security at Cloudflare. Who knows Cloudflare here? Nice. So I don't explain what we do. I'm passionate about security and crypto, and I also enjoy low-level programming. I like to dig into kernels, bootloaders, and other very scary low-level code. Okay, so before we start, so first of all, why do you ever want to consider a second CPU architecture? Well, why did we consider it? So there are a number of reasons. The first one is vendor lock-in. So I don't even explain it now. How many of you are running your code on non-x86 platforms? Mobiles do not count. Okay, yeah, cool. So not many people. How many of you run on non-Intel chips? AMD? Another one? Okay, so basically, most people run on x86, and Intel has 97% of the market share, so that's why you probably want to avoid it. The second thing is you might consider is energy savings. Some CPUs are more power efficient than others, and for example, this is a Cloudflare network today. We have like around 200 data centers across the world, and if we can save even a tiny fraction of power, probably we can power a small city with it, right? With power savings comes some money savings, and also we can cut equipment costs. So Intel chips or x86 chips are quite expensive. If you can find cheaper processors, you can like make your hardware cheaper in the overall. And for example, for ARM, there is more competition in the ARM market. There are more vendors. That's why you can have CPUs for lower price. And finally, this is security. Who doesn't know what this is? Yeah, this is a meltdown inspector, hardware attacks which were recently discovered on x86 architecture. Actually, ARM is also somewhat vulnerable to that, but like we started to think about what is the risks of there will be like, for example, another even more severe vulnerability discovered, and it will be unfixable, and we will have to shut down all our servers running x86. So at least if we have half of the servers in ARM, we may which will not be vulnerable, we will like stay in business, right? So why specifically ARM64? There are also many reasons. So it actually performs well in the mobile and IoT space. We all have smartphones. It's potentially more power efficient because it was actually developed for mobile and IoT space. It has huge developer community thanks to the smartphone area. So. It has first-class support in Linux. We run Linux in production, and most decent Linux distributions are now offering an ARM64 variant as a first-class citizen. So you have the full-featured distribution, and also you have established tools. You don't like back in the old days. You have to search dodgy websites to find like cross compilers for your embedded system. Now you can just download them from your package repository. Why ARM64? Because it's more than 32 bits. Probably you can still get away with 4 GB of RAM in your phone, but probably will not work if you're on a large server, right? And it somewhat mitigates the risk of the security vulnerabilities because it's a completely different architecture. So it's not like AMD versus Intel. It's like a completely different thing. So there is less risk that if the architecture vulnerability will be discovered in x86, it might not impact ARM so much. So this is some initial synthetic benchmarks. So we tested CPU from Qualcomm on the server market. So this is our current Skylake CPU we use in production. So we run some kind of Cloudflare-like synthetic benchmark. And as you can see, so this is our current generation of servers, this is our previous generation of servers, and this is the ARM CPU. And ARM CPU is actually not very far behind our current generation. So the current generation could do 16,000 requests per second in our benchmarks, whereas ARM could do only 15,000 requests per second. But we also measured power while we did it, and you can see that ARM used half the power to serve that number of requests compared to Intel. So it's actually quite a good initial benchmark. Yeah, we were very happy and saying like, yeah, we should definitely investigate it further. Let's put it in production. And when you put your ARM server in your x86 data center, you will see something like this. It will definitely not run well because it doesn't have all the software which runs on your x86 counterpart. So you go to your developers, right, and say, hey, developers, can you please, from now on, compile all your software for ARM as well, so we can have all our software stack on ARM. So, and when you start doing it, you encounter problems. So the first type of problems you will definitely encounter is compile time problems when you start compiling your software stack to ARM. The common misconception from developers is like, oh, we're probably not will be able to port our stuff to ARM because it has too much assembly, like architecture-specific code. In the reality of all the like hundreds of packages that we ported, we never were able not to port it just because of some kind of embedded assembly. This is never the case. The real problem for developers is that with the secondary CPU architecture, your production architecture does not equals the developer architecture, which they have on their laptop. So obviously you have some ARM production service, but developers still have x86 laptops, right? So they would definitely ask, okay, how do we even compile stuff for ARM? So you say, no problem. There is a thing called cross-compiler. Who doesn't know what a cross-compiler is? Everyone knows? So a simple intro. If you have this is a typical native compilation process, the regular compilation. You have some sources, you have a developer laptop, which is x86, you pass it, it has a compiler, you pass your source to the compiler, compiler produces the output, which you basically install into your production machines, this binary. And actually, developers can also run this binary locally because the developer architecture is the same as production architecture. With cross-compilation, it's a bit more complex. You still have your source file, you have the developer laptop, but instead it runs a special type of compiler. It's a cross-compiler, and that cross-compiler, although it runs on x86 architecture, it produces binaries for a different architecture, in this case ARM64. So you can install this binary on your production, but developers cannot run this binary locally anymore and test it because they have a different CPU architecture on their laptops. So to talk about cross-compiler issues, first we need to fix some terminology, and in cross-compiler terminology you have there are two definitions. You have the host architecture, with the architecture where the compiler runs. It's usually x86. For our case, it's x86. And you have a target architecture. It's a target architecture. It's the architecture for which the compiler produces machine code. And in our case, it's ARM64. And when you see these definitions, you'll just see that like regular compilation is a subset of cross-compilation, where host and target are the same architecture. So here is a simple example how to cross-compile a code. So imagine you have your source file, you just invoke your GCC compiler, it will produce a regular binary, you can inspect it and see that the binary was produced for x86 platform, and you can run it. To cross-compile the same code, you just replace your compiler with the cross-compiler. You'll get the binary. Again, you can inspect it. It will show that it was compiled for the ARM architecture now, and you cannot run it locally because your local operating system does not know how to execute ARM code. So the first issue we encountered with cross-compiling is if you take a source project for x86 and you try to build it for ARM, you get broken both native and cross-builds. So for native, I mean, we tried to cross-compile the project, but when we failed, we just tried to put the source on the ARM64 machine and just compile it natively ARM for ARM, and it still fails. And you get some error, which will probably look like this. From GCC, it will say unrecognized command line option. And the cause for this is probably because your build system has hard-coded architecture-specific flags in it. If you look into a build system, for example, I will produce makefile example. So in makefiles, you will see some like C flags or C flags defined to MSE2. So MSE2 is Intel x86 specific extension. So the GCC, which produces code for ARM64, will not understand this option because it's not applicable to ARM64. So if you're developing projects from scratch and you want to have a build system which is cross-compiler friendly, always put architecture-specific flags in a separate variable, and you should have one variable for each architecture. So something like this. So you have C flags for x86, you have C flags for ARM, and then when you compile your project, you generate the C flag depending on which architecture you're requesting it to compile. Another type of problems you might encounter that you have just broken cross-compilation build. So if you take the source and put an ARM64 machine and try to compile ARM to ARM, it will work, but it will not do, the build system will refuse to do cross-compilation, even though it might be designed to do cross-compilation from the ground up. And it usually happens when the final artifact is a result of post-processing of some intermediate artifacts from the compiler. So the compiler output is not a final artifact. And these additional post-processing tools are also included in source as part of your projects. And the error is quite similar. You get unrecognized command line option. So to illustrate what I mean here, imagine you have some sources, you compile it with the compiler, you get some intermediate output, and then you have some additional tools we need to post-process this output. In this case, you compile it with a different compiler because you need these tools as part of your build system and not final artifacts. Then you get these tools, and the final step is you post-process these intermediate artifacts, and you get your final artifact. This is a typical setup of, for example, if you're building a bootloader for Linux like grub and iPXE. So the cause is the build system uses generic C flags for building. And instead of using like target C flags and host C flags. So if your build contains both building code for target architecture and and host architecture, you should separate the flags in different variables. Or in our case, we tried to build iPXE. iPXE build system actually supports cross-compilation from the start, but it never worked for us. It was broken because they have this separation, but they use additional common C flags, which were only based on the target host. So this is like the example from iPXE. This is how their build system was set up. That's why it didn't work for us. And so for developers, again, the advice is you should put your architecture-specific flags in a separate variable, one for each architecture, and also always prefix any compiler linker options with target or host, because when you modify your build system, you'll clearly see if these compilers flag are for binaries for the target architecture or for the host architecture. DevOps can help here as well. So in case of iPXE, the build system supported cross-compilation, but it was fundamentally broken because probably they never tested it. So if you have some kind of CI infrastructure, even if you don't need, if you plan to have to use cross-compilation in the future, start testing the cross-compiler build from the start. And probably you can design some kind of linters and scripts which will scan project build system for non-prefix variable definitions, which do not conform to the advice I have given you before. Your developers would definitely complain, why are we building like for ARM64, we still don't use it, we have slower build times, but I think it's a feature because you give your developers a chance to have a rest from their daily hard-working routine. The final symptom we encountered is broken artifacts. So both native compilation and cross-compilation works, but the output of the build system is just broken for the target architecture. Again, as in the previous case, it usually happens when the compiler outputs needs additional post-processing tools. These post-processing tools are included in source as part of the project. But also these post-processing tools are released as an artifact. So you need these tools both during the build, and you also need to release those tools as a final artifact. And you get a error. Finally, when you release those artifacts, you will get error saying something like that. You cannot execute binary file exact format error. So the cause here is incorrect usage of the compiler. So you process your target artifacts with an invalid compiler. You process it with your host compiler. And sometimes it happens when you incorrectly declare build dependencies in make files. The example we encountered is actually in a big popular project, vanilla Linux kernel distribution. They have scripts to produce Debian native deb packages with the output, and it produces broken Linux headers Debian package when you do cross-compilation. So to illustrate what I mean here as a setup, so they have similar setup as in the case before, but they have this additional step where they do extra packaging in the end. Here is like the Debian packages being produced for the target architecture. And the problem was in fixdep utility. So it's a simple tool which does post-processing of the compiled kernel modules. So you can actually need it during the build system, the build stage to post-process the modules you're building, and also you need to package this tool into your Linux headers Debian package so you can later build third-party kernel modules on your target architecture. But unfortunately, Linux build system packages fixdep compiled for x86 architecture into the ARM64 Debian package. So the advice here is you should ensure that all dependencies are, all artifacts are processed with your target compiler. And the good practice here is actually in many embedded projects, if you separate outputs by folder, you separate your host output. Your output contains two folders, host and target, and your host output binaries go into the host folder, and target output binaries go into the target folder. If you ever compiled Android, they actually do this way, and it's quite convenient. For DevOps, you also can test, as in the case before, you can test the cross-compilation in the CI. Additionally, you can also do some tools to inspect the final artifacts for anomalies. So, for example, if we had a tool which will scan the Debian package for ARM and it finds that it contains x86 executables, there is something wrong here, right? So we can like catch it early on the build stage. Okay, now we compiled everything, and now we go into runtime problems. So we compiled all our software and tried to run it in production, but it's not as easy. Is it me? Sorry. So the first symptom we encountered is one of our database workload complains about not being able to allocate memory. And actually, when you log into the system and check, there is plenty of free memory in the system. And most likely, this process is using a map system call for file system I/O. Most database workloads do that. And you get error something like that. Mem cannot allocate memory. So to understand this problem, let's go back. Why did we move to 64-bit architecture? So 32-bit architectures allows us to address up to 4 gigabytes of RAM, right? So the 64-bit architecture allows us to address up to this big number, more than enough RAM, right? So that's why we will use 64-bit now, because like 4 GB is definitely not enough for modern servers. But actually, your operating system, all operating system trick you, steal your address space. So for example, if you take Linux memory layout for x86 system, you will see that it will only allow your application, which runs here, to have 47 bits of addressable space, and you have like this unused range, which no one uses, and then the upper addresses are reserved for the Linux kernel itself. Here is the documentation if you're interested. So on x86 system, actually, all your process can have only 47-bit of addresses in user space. So it's not this big number, it's like 132 terabytes, but it's still more than enough, right? Like 132 terabytes. However, on ARM64, you have a different memory layout. And if you take Linux default, which we did initially, you will get only 39-bit of addressable space. And the problem with that, you only have 512 gigabytes of addressable space. So in our case, we had a database workload, and for storage, we allocated the whole disk for this database. So the process tried to map the whole disk into memory, but if your disk is larger than 512 gigabytes, you don't have enough addressable space. So your mmap call will fail, and Linux will say that it cannot allocate memory, although it actually doesn't allocate any memory. So for developers, we should try to avoid using unbound memory mappings. Although it's hard, if you plan to map a very big file in your code, try to identify the upper bound of the user space, addressable space. There is no like portable way to do that, but it's certainly possible to do it in Linux, for example. For DevOps, we need to make sure to review your second architecture kernel memory layout configuration. And you might need to recompile the kernel for that, which we did, actually. So we have chosen a different memory layout for ARM64 kernel, and which provides us with 48-bit of user space addresses. And that gives us 256 terabytes of addressable space. So we fixed that database workflow, but some other workflows started to crash randomly. After like a very long debugging, we traced it down to Lua code. In Cloudflare, we're heavy users of Lua as some of our business logic on the edge. So introducing you the so-called Lua JIT light user data module. So we use Lua JIT obviously to make Lua faster, and some of the Lua JIT internals use this module, which is basically a simple, efficient C interface. This is how Lua code and C code interact with each other. And efficiency comes from the fact it operates directly on C pointers, so it stores C pointers in Lua variables. However, they tried to be smarter, and with C pointers, they also needed to store some metadata for, like, I don't know, internal bookkeeping. And they noticed that, hey, on 64-bit platforms, we only have 47 bits of addressable space. So that means all upper bits are always 0, so we can use them to store our metadata. Because it's always 0, right? So this is the code, and you can see it in the comments, right? So 32-bit platform and 64-bit platform layout, we have always 47-bit pointers. But if you remember, on ARM, we have 48-bit pointers, right? So like that's why the workload randomly crashed, because sometimes this upper bit, one bit was corrupted, and the whole process went down. So for developers, I mean, this was very, very hard to find. So state your assumptions in code and not in comments. And probably you can check your assumptions early and error out with a meaningful error message. So if you want to rely on the assumption that your code, you have 47 bits of addressable space, when your process starts, check it immediately, and if it doesn't, your assumption doesn't hold, error out saying like, sorry, I can't run on this platform because I assume you should have 47 bits of addressable space and not more. This was also a clear case of over-optimization. So if you want to over-optimize and save these tiny bits of space, it's a good idea also to provide a fallback, less optimal generic implementations for when your assumptions do not hold. Same goes for DevOps, actually. There is no separate advice here. Another interesting type of optimization is page size. So like if you look into different software and they want to optimize performance, it's usually something around page size. So what is a page size? It's a minimum discrete block of volatile memory on your system. And many database workloads, again, try to keep track of the allocated pages. They do it for different reasons. The most common are they have faster memory access. They want to do sequential memory access. They want to avoid memory fragmentation and also efficient memory reuse, not to use the system allocator all the time. So they just allocate some pages and keep track of themselves, which pages are needed and which pages are not needed. So the symptom here we encountered is the process uses much more memory on secondary architecture. However, otherwise it doesn't crash. It actually works as intended, although it may be different for different workloads depending how aggressive the code is with this memory management. The cause for this is usually the process has hard-coded page size. But the target architecture has a different page size. So most people just assume that the page size is always 4 kilobytes because an x86 system you can't have a different value, at least like in Linux. Whereas in ARM you have this, you can reconfigure your memory layout, which we did earlier to fix other issues. And to get to 48-bit of addressable space, we had to change the page size to 16K. So what you get in result, something like this. So imagine this is the perfect case for a database workload for 4K page size system. So you have the sequential memory, you have you allocate continuous pages, and then you start using them. If you run the same code on a 16K page system, you might get, in worst case, something like this. So you kind of already lost all you've been fighting for. So you don't have sequential memory access, you have memory fragmentation, and you don't have efficient memory use, right? You waste like 4 times the memory. But developers don't do this. So more than 14,000 exact matches on GitHub with this string, potentially broken for other architectures. Instead, just ask your operating system, what is your current page size? So it's easy to do. For DevOps, we should definitely monitor process memory usage on different architectures to find issues like this. Next is file system block size. It's like page size, but for files. So it's the minimum amount any piece of data can occupy on your file system. For example, if you create a 1-byte file, because the file systems are usually located on block devices, your 1-byte file will still occupy that block bytes. So it's usually called the physical file size, and this called the logical file size. And in most cases, it's not important, and this block size is usual, some kind of multiple of underlying block size of the underlying device. The typical values you might encounter are 512 bytes or 4K, depending on which disks you use. For Windows world, I think it's called like the cluster size when you format your file system. And it's most of the times you don't need to care about physical block size, except for one case where you care about sparse files. So do you know, does anyone know what a sparse file is? Or yeah, so usually any file has physical block size larger than the logical block size, because you can't, even 1 byte text, at least block size. Except for the sparse files case, where modern file systems are now smart enough to say, if you have a big file which is largely have zeros in it, it will not write zeros to disk. Instead, it will just write a marker that this range is all zeros. So in the end, you have the physical file size, which is smaller than the logical file size on the file system. So the symptom for us was the sparse file test failed on ARM64. It's from the open source Captain Proto library. We use Captain Proto in our logging pipeline. So I tried to run the test suite, and it fails for ARM64. The interesting part I noticed that this test fails only when the test suite is run from TMPFS. So I run it on TMPFS, it failed, but when I accidentally run it on a regular like storage back file system, the test succeeded. And the cause was that the process had hard-coded block size in the test code to 4K. But if you remember our discussion about page size, on memory-backed file system, your file system block size equals to the RAM page size, and we run on ARM64 on 16K page operating system. So we had this scenario. So the test failed because it couldn't create a sparse file, because it assumed that the underlying block size is 4K, and when it created a file, it actually was not smaller than, the physical file size was actually not smaller than the logical file size. So don't do this. Ask your operating system, ask your file system, what is your underlying block size? Yeah, so that's basically it. This all the potential things we encountered. So here are some conclusions and to repeat myself, we had all these issues and we never encountered any code which we couldn't port because of the assembly instructions. So even portable code with no assembly can fail in many ways on a different architecture. The advice for developers is don't over-optimize your code, provide fallback implementation, try not to rely on assumptions, and if you have to rely on assumptions, better to check them in your code rather leaving them in comments, and also provide meaningful error messages to the users if your assumptions do not hold. Because again, it's very hard to debug if you have an error message that cannot allocate memory if there is plenty of free memory on the system, right? For DevOps, try to create CI environments or CI/CD environments which can test diverse architectures and configurations. So try to test cross-compilation, try to compile, at least have your builds working for different architectures. It will surface many edge cases. And also you can design tools on linters to enforce best practices for code and build system, which I just described. Hopefully my advice will be useful. So after we overcome all these issues, here is how ARM server looks now in production. It's almost indistinguishable from its x86 counterparts, and sometimes when like an SRE logs in to do some maintenance or debugging, they often don't even notice that they were doing this on the ARM64 server. So yeah, that's it. Have time for questions, if you have any. Можно на русском.
Вот эти вот чудеса, которые вы описали с размером блока и так далее, я думаю, что они очень старые на самом деле, тянутся еще там чуть ли не с времен Торвальдса. И как могло так получиться, что при этом, как вы сказали, huge community и все такое, вот такие какие-то просто анекдотические ляпы присутствуют и до сих пор не пофиксены тем же комьюнити. То есть спасибо вам, что вы их нашли, что вы нам рассказали, но...
Ну, скорее всего, опять же, исторически эти чудеса тянутся со времен Торвальдса, но много и мы очень много используем open source проектов, и много open source кода тоже тянутся с времен Торвальдса и при этом. К тому же сейчас не так уж и много компаний, которые имеют в своем распоряжении ARM сервера, правильно? То есть ARM всегда была архитектура для мобайла и IoT, никто не гоняет мощную базу данных на ARM сервере. И как бы этот рынок только зарождается, то есть только сейчас компании производят процессоры, которые могут конкурировать более-менее с x86 архитектурой. И, кстати, еще касательно ARM, который не 64, он очень был, скажем так, разнородный. То есть если вы зайдете в код Linux, вы посмотрите, что у Linux, даже в коде Linux есть очень много разных папочек или конфигураций для разных ARM-бордов, потому что каждый борд делал какую-то свою архитектуру. И только в 64-разрядном ARM они как-то там стандартизировали, что оно такое, как вот x86 PC-compatible состояние, что все борды, они там примерно одинаковые. То есть, грубо говоря, просто никто этого раньше не использовал. Все гоняли на x86 и никто не тестировал.
А какие приложения вы вообще запускаете с ARM64 архитектурой? Работают ли они в продакшене, либо...
Ну, у нас сейчас несколько серверов есть в продакшене. То есть весь наш программный стек был портирован на ARM. То есть иду снизу вверх. То есть,
это сетевые сервисы какие-то?
То я сейчас могу пройтись по всему стеку. То есть внизу это бутлодер наш. Мы чуть-чуть модифицируем iPixel. Ядро тоже мы собираем с исходников, как бы с нашей конфигурацией, немножечко патчами. Ну, Debian мы используем стандартный Debian, кстати, базовая операционная система ARM поддерживает. И сверху у нас ядро всего нашего мозга — это Nginx, и очень много кода на Lua. То есть вот это. И сопутствующие сервисы, которые поддерживают всю сетевую, мы пишем сами, и они в основном написаны на Go. То есть, в принципе, вот Go, допустим, очень кроссплатформерный язык, но вот половина из этих проблем именно пришли даже с Go-программ, потому что они тоже делали вот эти ассампшены про операционную систему, что у тебя есть размер страницы памяти 4К и так далее.
Еще такой вопрос, немножко не по теме. Запускаете ли вы в Kubernetes что-то в ARM64?
В ARM64 еще нет. Но у нас есть уже для этого этот CI. Мы как бы готовимся, но пока нет. Ну, как бы у нас очень большая распределенная сеть, но у нас есть еще пару дата-центров, которые хостят наши внутренние сервисы. То есть наши сервера, которые находятся по всему миру, у них очень простой стек. Там нету ни виртуализации, нету ни какого контейнерного, скажем так, контейнерной оркестрации. А вот наши внутренние сервисы, где сопутствующие, где разработчики запускают внутренние сервисы для поддержки этой инфраструктуры, там Kubernetes сейчас, но он пока только на x86.
Заметил у вас в вакансиях, год назад где-то появился Kubernetes. Раньше, по-моему, был Mesos.
Да, раньше мы мигрируем с марафона, Mesos марафон на Kubernetes. Так что, если интересно, приходите.
Спасибо.
Можно я повторю, если что.
Спасибо вам за доклад. Пользуюсь вашей компанией, очень классные у вас продукты. Вопрос в следующем. Во-первых, интересно, по вашему железу ARM64, какой вендор у вас или что за железо непосредственно используется? То есть какое-то вендорное, кто производит сейчас такие сервера?
Мы только на зачаточном состоянии, то есть мы больше общались с производителями процессоров, а производители процессоров дают тебе как бы тестовый сервер, чтобы ты мог попробовать. Но как бы потом, когда все это развивается, мы еще не перешли в стадию, где мы говорим: хорошо, мы возьмем этот процессор, и теперь мы идем к какому-то вендору, и они нам под нас делают какое-нибудь шасси. Да? То есть по процессорам, вендорам, то есть мы говорили с Qualcomm, но они, по-моему, сейчас раздумывают, может, они перестанут производить эти серверные чипы, что-то. Они Как-то у них бизнес, по-моему, поменялся. Есть еще Cavium и третий. Не помню, какой.
Я понял, то есть сейчас никто не производит, в принципе, каких-то готовых решений, таких, чтобы можно было купить. И второй вопрос, в чем вообще заключается смысл? То есть это какой-то профит в финансовом плане получается, производительность по меньшему прайсу, если используется, да?
Да, где-то так и есть. То есть тут есть два главных вопроса. Это производительность и меньшее энергопотребление, за которое надо очень много оплатить. И второй вопрос – это риски безопасности. То есть мы сначала так очень думали, запускать ARM-проект или нет, но когда Meltdown и Spectre вышли, мы сказали, надо стараться запустить что-нибудь еще, хотя бы, чтобы в случае, если будет еще одна такая уязвимость, которую просто нельзя будет никак починить, и она дойдет до уровня того, что все, вам надо потушить все ваши x86 сервера, то у нас хотя бы половина будет на ARM. То есть мы все равно останемся на плаву.
Да, я понял, спасибо вам.
Вопрос был, я повторю для записи, есть ли у нас сейчас избыточность ARM-серверов, чтобы покрыть всех клиентов? Нет. Мы еще так...
В теории хотите дойти до состояния, что можно потушить половину серверов, и второй половины хватит для обслуживания всех клиентов?
Возможно. Я больше разработчик, я не буду четко говорить про финансовый план. Но если это будет финансово выгодно, то, конечно, дойдем. С точки зрения безопасности я бы хотел оказаться на таком уровне. Но получится оно или нет, еще пока непонятно. Интернета может на всех не хватить, если все x86 сервера потушат. Все? Да. Что? Еще раз.
Виртуальное окружение, эмулировать ARM64 при помощи Кеву.
Вопрос был, рассматривали мы QEMU, чтобы эмулировать ARM64 архитектуру. Да, и мы очень ее сильно используем. У меня, кстати, есть доклад по этому поводу с того года, по-моему, SRECon в Сингапуре. Он похож на этот, тоже он про ARM, но именно как мы использовали QEMU, чтобы запустить всю нашу целевую аудиторию. То есть у нас было два вектора. Первый вектор мы использовали полноценные виртуальные машины, но они достаточно медленные, особенно если вы компилируете тяжелый проект. Второй вектор это мы немножко пропатчили. Есть еще в QEMU такой режим User Mode эмуляция, если вы знаете. Не слышали про такое? User Mode — это когда у вас не полноценная виртуальная машина, а у вас есть интерпретатор ARM, который работает на x86. То есть если у вас есть исполняемый код под ARM, вам не надо полную виртуальную машину заключать. Вы запускаете этот интерпретатор, кормите туда этот бинар, и он выполняется на вашей x86 машине. То есть, но это как интерпретатор, то есть его надо каждый исполняемый файл специально запускать через этот интерпретатор. Что мы сделали? Мы там усовершенствовали один блок, который я у другой компании нашел с 2015 года. Мы пропатчили QEMU, и с помощью нее мы создавали специальные докер-контейнеры для разработчиков. То есть разработчик не устанавливает полноценную виртуальную машину, он просто запускает контейнер, но когда он входит в середину контейнера, там ARM окружение. Оно имеет, конечно, свои ограничения, потому что оно все равно использует x86 ядро, то есть некоторые эти проблемы вы там не поймаете. Но для такой базовой разработки, компиляции и запуска простых приложений оно очень подходит.
Спасибо.
Все,
Игнат, большое спасибо.
Пойдем пить кофе.
Аплодируем нашему спикеру. У нас получасовая пауза, продолжим через полчаса в этом зале погружаться в software architecture. Да, сейчас